Professor Saykally will be the fourth speaker. And as this overhead view graph shows you, the entire colloquium was put together as part of this Water Resources Center archives, which is a library devoted to unusual but rare materials about water in California and the West. Just to educate ourselves, the faculty, the students, as well as the public, about water in general, not water as just as a commodity or something to fight over, but water in general as something which is so unique on this earth. And so each semester we try to have 4 speakers from 4 areas of human knowledge: humanities, social sciences, engineering, and natural sciences. And today Professor Saykally, who is a distinguished chemist from our chemistry faculty, he is going to talk about this fascinating and mysterious thing called water. Why water is the way it is. It is so fundamental to life and to the earth itself. In all the solar system, there is nothing like the earth anywhere. This is so unique, and largely because of water. And despite the fact that water has been part of our lives for billions of years, we still have not figured out how water works the way it works. And fortunately, that keeps a lot of research money for our professors of physics and chemistry. It gives them a nice opportunity to do a lot of research. And Professor Saykally, who is a physical chemist by training, physical chemistry is the branch of chemistry devoted to understanding the structure of materials and the behavior of materials. And for his work, he has been recognized by election to the National Academy of Sciences in 1999, which is our premier scientific institution. And he has very kindly consented to come today and share with us their latest research and their latest understanding and the latest ignorance about how water works.
Thank you, Neri. It's a real honor to come and talk to a diverse audience like this. And from looking at the previous lecture titles here, I can see that I'm going to take a much more fundamental point of view than what you have heard in the past. For example, the first lecture had the title, "Are we going to run out of water in California?" Perhaps that touches on this subject. For those of you who, in a very practical sense, if you walk around anywhere on campus, you are likely to encounter this. At least half the people here will encounter this specific thing. But this shows the water policy situation in California. If you read these little stickers that are everywhere on campus, they say this. So 10 years ago, people were going around putting up these stickers on every facility and every washroom on this campus that said, "Conserve water." We were in a terrible drought, all of that. And then last year, we had quite the opposite reaction. People got tired of the messes and all this, and then they went around and says, "Please flush." So all of the facilities, you can take your choice. But it's only a matter of time until we go back to the conserve water perspective. Anyway, as you heard about in the practical lectures. So that's the only practical thing I'm going to tell you. We're going to take a much more fundamental point of view here on water, and let's start from the beginning. Let's ask the very first question: what is water? And actually, I've been interacting with lots of small children lately, trying to give little shows at schools and stuff like this. And one can collect a lot of interesting responses to this question, what is water? Here are some this is real live quotes from 11-year-old science exams. So here's one. H2O is hot water, CO2 is cold water. This is absolutely true from science. But at least they understand that these are the two most important molecules on Earth. But this one's better. Oxygen and nitrogen. Real coke. No However, my daughters who are sitting right there, along with my wife Chris, are more advanced than this. Here they are at an earlier age, and they can answer this question, what is water? Of course. What is water, girls? They said they would be absolutely mortified if I showed the picture of them in the bathroom. What is water, girls? Not good. Okay, so we all know water is H2O, right? So then the essential question is that came out of the bathtub also. Daddy, what makes water wet? Who asked me that? Which one of you asked me? What makes water wet? What's the answer, girls? Let's give the answer away at the beginning of the lecture. What makes water wet? Julia, what makes water wet? Huh? What makes water wet? Not going to be much help. Okay, they won't give away the punchlines. So you'll have to endure the whole lecture here until you get to the end of this. They're not going to. So they made this sort of theme slide up for me a long time ago. Water is H2O, and we're going to learn about what makes water wet. So let's remind ourselves what are the, well, before that, this is a different audience than I usually deal with. I usually am talking to hardcore physicists and chemists who would never let me get past this statement here. What makes water wet? What would you do? What would you answer if your children said to you, what makes water wet, Daddy? What would you say?
I'll have to think about that one. That's a tough question.
How about you? What would you say?
Must be water and hydrogen.
Water and the hydrogen. How about you? What would you say?
I have no idea.
See, this is a very different audience, because these really hardcore guys in my business would say, well, no, wait a minute. Wait a minute. First you got to tell me by what you mean by wet. They would never let me get past that point. Does anybody want to know this?
Yeah.
You want to know what I mean by wet?
Yes.
Come here. So we have prepared a little demonstration for you. This is a good day for this demonstration. Me first. This is my H2O bag. You can buy these H2O bags. You can buy H2O hats, shirts, jackets, boots, umbrellas. This is the Adidas company of Copenhagen. So one way to tell you, here's what we mean by wet. This is how I answer this to my physical chemistry colleagues. This one doesn't work very well. So let's show them what we mean by wet, girls. Here, go show here. You start over there. You start over there. You go over there. No, I'll go over here. Put something hot down. Shoot down! All these things are malfunctioning. Okay, well, Let's see how this is going to work. Show them what water, what it means. Who wants to know what it means to be wet? Those guys back there.
Ryan wants to know.
Okay. So this is very nice when I give this lecture to physical chemists. This quiets them down. But, so back to science. Let's talk about what I mean by wet in a scientific sense. Refers to the properties of water, which Neri said are very unique. It's amazing. We live in the midst of this substance and we take it for granted, but it turns out that water as a molecule is truly a singular substance. And even Mother Teresa, featured on the cover of this magazine, says H2O, what you should know about H2O. So here's what we should remind ourselves about water. The first fact that is extremely important and seemingly, hey, put that away, seemingly really commonplace is the fact that ice floats. There's one other substance for which the solid floats on the liquid. And that substance is a very strange alloy between bismuth and... Okay! I know what makes water wet. They don't. Okay, thank you. Thank you. Okay, come on, thank you. So, thank you, girl. So here on this picture, you see all three common phases of water. Ice, gaseous water in the clouds, and liquid water. And the ice is floating on the liquid. The only other substance for which the solid floats on the liquid is an alloy of bismuth and antimony used in the printing industry. This is very unusual behavior. Solids are always denser than liquids, except for water. But it seems so commonplace. Here's another thing we encounter often, at least if you're skiers, snowflakes. And snowflakes, if you study them carefully, all have hexagonal symmetry, six-fold symmetry. Why is that? Interestingly, these two questions are related. Ice floating and the hexagonal properties of snowflakes are related. They have the same cause. Here's a picture from a biology textbook that illustrates this business about the solid floating on the liquid and some other properties more dramatically. Here's ice floating in liquid water. Here's ethanol, ethyl alcohol. There's the ice sinking. Ethanol is about as similar to water as you can get, and yet its solid sinks. This is oleic acid, basically French fryer grease or something. There's the solid sinking in the liquid. Very unusual behavior for the solid to float. Here's another interesting thing, surface tension. The surface tension of liquid water is very high compared to normal liquids. And you can float, if you very carefully put a spoon on the surface of liquid water, the surface tension will hold the spoon as shown in this photograph. Whereas if you try to do this in ethanol, again, about as similar a substance to liquid water as you can find. It sinks, and likewise in the grease.
Are these at similar temperatures?
Yeah, these are all at similar temperatures. So, and there are other. Water is truly a unique substance. This is a phase diagram. How many of you have looked at phase diagrams? Many of you are familiar. This phase diagram shows the pressure-temperature relationships between the three common phases of matter: solids, liquids, gases. Solids appear at high pressure, low temperature, etc. And most substances have three phases or a few phases. Maybe there'll be a couple different kinds of solids, but very few phases. They'll have a solid, a liquid, and a gas. Maybe a couple different forms of the solid. Here is an old phase diagram of water. There's the liquid region, there's the gaseous region, and this is the solid region. And it's very complicated. There are actually 15 known forms of solid water. Ice 1H is the name right here for the common form of water, H meaning hexagonal. 15 known forms of water to date, and I'm sure more will be found in the future. Here are two of these. Here are two really interesting forms of water. This is what we call amorphous ice. It's like a glass. It is a glassy state of water. There is no long-range crystal structure. This is LDA, low-density amorphous ice. This is high-density amorphous ice. There's a very interesting demonstration that I've seen a couple of times by a person from Scuba Research Institute in Japan who has made a film here. He makes high-density amorphous ice, takes it out of the high-pressure container, sets it out in the room, and then explosively makes a transition to this form. It blows up very violently. These are two of the 15 forms of solid water. Here is the latest of the 15 forms, published in 1998. Some very beautiful high-pressure work from Russell Henley and his group at the Carnegie Institute in Washington. Here's the reference, Science 1998. A new high-pressure phase of ice. This is what it looks like. They call this Ice 12. And here's another publication. This is what it looks like. You see this very unusual kind of symmetry. This is a very high pressure phase of ice. Ice 12, I said there were 15 forms. Okay. There are 12, there's two forms of ice 1. There's ice 1H, the common form, H meaning hexagonal, and ice 1C for cubic. So there's two forms of ice 1, and then there are the two amorphous forms. That adds up to 15. Ice 12 is the highest name. 15 forms of the solid. Very complicated behavior.
What is the highest temperature you can have ice? Given sufficiently high pressures, what is the highest temperature?
Yeah, let's look at that question. Okay, so here's the phase diagram. So here are, this only shows things up to ice 6. So when we get up to 8,000 atmospheres, you can see this curve going up this way. So I don't know the answer to that, Mary, but it's probably...
70 or 80 degrees?
Yeah, it looks like that. It looks like it. If you see where this curve is going. Pretty high temperatures. Pretty high temperatures. Okay, and these 15 forms of the solid don't even include this other form. Now this picture here is used by many people in chemistry these days when they start talking about the new form of carbon that has romanced much of chemistry, the fullerenes. Fullerenes are the third form of carbon, the third allotrope of carbon that's built on an architecture of 5- and 6-membered rings. Specifically, I have exactly 12 5-membered rings. By Euler's theorem of solid geometry, I can form closed surfaces like a ball. And a ball can actually, this soccer ball is actually formed from 12 5-membered planar rings and 20 6-membered rings. But there's a whole architecture of carbon based on this sort of thing. You can build arbitrary shapes and arbitrary sizes of pure carbon molecules from exactly 12 planar 5-membered rings and an arbitrary number of 6-membered rings. Okay? These are called the fullerenes. The Nobel Prize in Chemistry was given in 1996 for this discovery. Smalley, Cordell, and Curl. Well, there's a whole architecture of water based on this too. They're called clathrates. Same idea. You can take 5-membered rings of water and 6-membered rings of water, and you can build a whole architecture of arbitrarily complex geometrical objects that are hollow inside. And of course, many of you know that in the last couple of years it has been recognized that these clathrates, these are just pure water molecules now, with the hollow cages. These clathrate molecules containing methane on the inside are now recognized to be the single largest source of hydrocarbons on the Earth, a larger source of hydrocarbons than the oil or the coal or the natural gas. Nobody has figured out how to get them. They're found in the deep ocean trenches and in the Alaskan and Siberian permafrost. Nobody's figured out how to get them out and use these yet. But anyway, this is another whole solid architecture of water. It doesn't even count in the 15 forms of ice yet. Okay. These are very interesting. You'll surely hear more about water clathrates in the future. Okay, so summarizing some of these things, water is a very weird substance. Ice flows, it actually has a density maximum at 4 degrees. There are 15 known forms of ice. The properties of water are strange. We will say more about that. And without these unusual properties, life would not be possible the way we know it, as stated by Professor Look in this book. So, in a practical sense, here are some aspects of water that are common to us. 0.023% of the Earth's mass is water. That translates into 6 times 10 to the 10 gallons per person. 70% of the Earth's surface is covered by water. Actually, more like 80% if you count ice, solid and liquid water. About 80% of all living cells are composed of water. The early scientists recognized the importance of water in their periodic table. We all know that. And the unusual properties of water, here's a picture from an introductory biology text, which is a little too complicated to go into now, but it shows some of the things that we take for granted in life. Water and soil for plants and aquatic life on the surface of lakes depends very strongly on the surface tension, the very high surface tension of water. Winds and storms and regulation of human body temperature, animal body temperature, depend on the very high heat of vaporization of water, unusually high. The heat capacity of water is unusually high. This is the ability to store heat. It's measured by this quantity called heat capacity. That manifests itself directly in having a very narrow range of planetary temperatures. The temperature of our planet is strongly regulated by this presence of water.
Heat capacity is also responsible for El Nino.
There you go.
Because the Pacific Ocean stores a lot of heat.
Yeah, and our weather depends very much on this. Okay, so to summarize some of these considerations, what makes water wet? By wet, I mean the properties of water. The unusually high boiling point, unusually high melting point, high surface tension, high heat capacity. Ice floats on the liquid, very unique. There are 15 forms of the solid and other properties, very unique. What makes water wet? What's the scientific answer? We all know. Somebody tell me. What would you say if you were
shaking the molecule?
close? There's two words that answer, that people tend to answer this one. What makes water so unusual? What gives water its unusual properties? I heard it. Hydrogen bond. That's the answer. Hydrogen bond. Water is a strong hydrogen bonding substance. Let's explore this. Every freshman chemistry textbook has this figure in it as an example of hydrogen bonding. What we're looking at here are boiling points of simple substances as a function of position on the periodic table. Okay, here's what we would call simple regular behavior. These are the rare gases. They're spherical atoms, liquids of those. These are the boiling points of the rare gases. The larger rare gases have higher boiling points, and as you go down the periodic table from you're going up the periodic table starting at xenon, krypton, argon, neon, to the lightest helium, the boiling point is decreasing monotonic. That's regular, normal behavior. See the same thing in these hydrides, methane, silane, germane, stannane, regular behavior. When you go to the ammonia, the group 5 substances, phosphine, arsine, again you see regular behavior until you get to ammonia. And ammonia is way off this graph. Now let's look at the halides. HCl, hydrochloric acid, HCl here, then we go to HBr, HI, regular behavior there, but HF jumps way off. And likewise in the water series, hydrogen sulfide, hydrogen selenide, tellurium all behave nicely, but water jumps way off the graph. In the standard explanation, elaborated in every freshman chemistry text, is these 3 substances are the prototype hydrogen bonders. Those 3 molecules, water, hydrogen fluoride, and ammonia, are the 3 examples of strong hydrogen bonding that we're talking about. This is what the structure of simple solids and liquids is. You can think of a normal liquid like liquid argon or liquid xenon as basically being a bunch of marbles in a beaker. There's no long-range order here. There's short-range order, but no long-range order in that beaker full of marbles. When you go from the liquid to the solid, you can think of spending a lot of time stacking up these marbles in a very careful way. And that's what happens when you freeze the liquid. You get long-range order. This is a close-packed lattice. This is the simple, regular behavior that most substances exhibit. Ammonia behaves like this. This is what ammonia, the picture of ammonia looks like. Even though it's a hydrogen bonder, it behaves more or less like a spherical molecule. HF, hydrogen fluoride, the other prototypical hydrogen bonder, actually has structures like this in liquid. It tends to make one-dimensional chains that can branch, but they're primarily one-dimensional. Here is the big difference between hydrogen fluoride, ammonia, and water. They're all strongly hydrogen bonding, but HF can only act as a single donor of a hydrogen bond and a single acceptor. Ammonia, actually that's not correct, it can act as a single donor and it can accept 3 hydrogen bonds. Ammonia can donate 3 hydrogen bonds, but it can only accept 1. That means they can really only form basically 2 hydrogen bonds per molecule. Well, here's where water is really different than even these other strongly hydrogen bonding systems. Water forms strong tetrahedral hydrogen bonds, and here's why. So the structure of the water molecule is like this. It has 2 lone pairs of electrons and 2 hydrogen atoms bonded to the oxygen, and the angles between the hydrogens and these lone pairs are all approximately the tetrahedral angle, 190 degrees. Actually, it's 104.5, close to the tetrahedral angle. So that when water hydrogen bonds, it can actually form 4 hydrogen bonds. Water can donate hydrogen bonds from these slightly positively charged hydrogens, and it can accept 2 hydrogen bonds from other water molecules at those lone pairs. And all the angles will be tetrahedral. So water forms 4 hydrogen bonds in solids and liquids at the tetrahedral angle. This is what's different between water and hydrogen fluoride and ammonia. This is what's responsible for all the strange behavior of water in a nutshell. So it's hydrogen bonding is part of the answer, but strong tetrahedral hydrogen bonding is the total answer as to what makes water wet. This is what my daughters were supposed to tell me. So what makes water wet in summary, girls? What makes water wet? What do you tell your teachers? Well, it was a long day last night. Mosquitoes. So, this strong tetrahedral hydrogen bonding manifests itself in the simple form of ice in this kind of a structure. So if we look at a given water molecule in ice 1H, the familiar form of ice, we can see that it makes 4 hydrogen bonds. So here are the hydrogens that belong to this water. You can see it's one there and one there. These are the covalent bonds of H2O. Now, it's accepting a hydrogen bond here and here, and it's donating one here and here. And all those angles are approximately tetrahedral, 109 degrees. 4 strong hydrogen bonds. Every water molecule in ice 1H does that. Now, if you orient yourself correctly on the ice crystal, you can look down these channels and you see 6-fold symmetry. You see these hexagonal channels that go all the way through the ice. And it's this is where the name hexagonal comes from. This is a 6-membered ring here. And it's this tetrahedral bonding gives rise to hexagonal symmetry. And that's why snowflakes have this 6-fold symmetry, because of this strong tetrahedral hydrogen. Here's a real space-filling model, computer model of what ice 1H, the simple form of ice, hexagonal ice looks like. There are the 6-membered rings. And the take-home message here is look at this lattice, and you will see there's a whole lot of empty space in it. And that's why there are so many different forms of ice. Because you can fill this empty space up in many ways as you start to apply more and more pressure to it. The ice will reconstruct to make denser and denser materials. Ice 1H, this substance, is the only form of ice that floats on the liquid. The rest of them sink. Okay, so that's why there are so many forms of ice. This is a very low density, inefficiently space-filling model. And there are many ways to compress this and make other structures. That's why there are 15 forms of ice. Here's why liquid is so complicated. Liquid water has these extreme properties, has extreme boiling points, extremely high surface tension, and other things result from the following very important fact. Here again is the structure of normal ice 1H, these 6-membered rings that are a consequence of strong tetrahedral hydrogen bonding. When I melt ice at 0 degrees centigrade, its melting point at 1 atmosphere pressure, only 10% of these hydrogen bonds are broken. In other words, in liquid water at 0 degrees centigrade, 90% of these hydrogen bonds that form the crystal lattice are still intact. So this is anything but a simple liquid. We have big extended networks and clusters in liquid water of these hydrogen bond networks, wherein 90% of the hydrogen bonds are still intact. That's what gives rise to all these extreme properties of the liquid. And that's what makes... Sorry girls, I borrowed something else from you here. They help me a lot. Water is trouble to the theoretical chemists and the theoretical physicists. For this reason, the liquid is so complicated. It has these hydrogen bonds extending over large regions of space. 90% of those hydrogen bonds still intact when you melt it at 0 degrees centigrade. Very hard to describe this theoretically. So, for example, one of the things that theoreticians focus on all the time when they try to model liquid water is to reproduce this feature here. This is the density maximum of water. Water has a maximum in its density at 4 degrees centigrade. So they try to do computer models of water that reproduce this. There's the density of the normal form of ice, much lower than that of water. That's why ice floats. They try to reproduce this. That's a canonical test of a water computer model. And here's the state-of-the-art look at it. There are about 1,000 published potentials for describing liquid water with computers. And none of them work better than this. Here's the curves. These red triangles are experiment, and these are computer simulations with a couple of potentials. It's very hard to get this right. Here are some other properties that you might care less about. This is why ice floats. Here's the compressibility of ice versus temperature. The red triangles are experiment, these are simulations. Take-home messages we don't do very well. Here's another property. This is the heat capacity, the ability of water to retain heat. It's very high. Here's the experiments, and this is what state-of-the-art computer simulations can do. It's not a very good picture. Okay. Why? What's the problem? Why is water trouble to the theorists? It is fair to say that we know everything there is to know about the individual water molecule. Here it is. Here's its structure to gory precision. We know this O, this is hydrogen oxygen. We know that bond length, gory precision. There's the bond angle. There's the dipole moment. We know everything there is to know about the water monomer. That's not the problem. The problem is we don't know how to describe the interactions between water molecules accurately. For example, we can't even describe this 5-membered ring of water molecules. This is from my group. Actually, ABC covered this for the conference sometime. We can't describe how 5 water molecules interact accurately yet, despite all the work. So let me just tell you rather quickly about some work that's going on in my research group in this effort. So what makes water wet? The cluster connection. So we're trying to answer this question, what makes water wet? In other words, what is responsible for the extreme behavior of the solid and liquid forms of water? We're trying to answer that by studying water clusters. Here's the motif that we have adopted here is this, building up the liquid one molecule at a time. So the idea is, we want to understand how water molecules interact. We want to understand this rigorously. So what we do in my research group is we have ways to make these individual water clusters of 2 waters, 3 waters, 4 waters, 5 waters, 6 waters, etc. And we can study these things in gory detail with a lab full of lasers. And that's exactly what we do. So here are some recent results. Here's the structure of the water dimer, that is 2 water molecules interacting. Here's gory precision on structure. There's a lot more detail that we have. Here's the water trimer. Here's the water tetramer. Here's the water pentamer. This 5-membered ring. That is the structural basis of clathrates. Here's the most stable form of 6 water molecules. It's not a ring. All the 3, 4, and 5 are rings, but in their most stable form. But 6 is not. It's a cage. The way we make these water molecules is by tricking nature. Here, half of you are engineers, right? So you know all this stuff. The way we make these water clusters is by tricking nature by forming what we call supersonic beams. Basically, you expand the gas in this case is argon bubbled through water, through a small orifice into vacuum. And if you do this right, you can do this in such a way that the only way molecules can get out this small hole is if they all line up and go exactly in the same direction with the same speed. And when they do that, this is called the supersonic expansion. When they do this, the temperature in this beam drops extremely low. And temperature is a measure of relative motion of the gas phase. That's how we define temperature, relative speed. So if you're a molecule and you're moving along here and you look at your neighbors, they're all moving the same way, at the same speed, and in the same direction. So the temperature is extremely low. It's just a little way to trick nature to make directed mass flow, as it's called, an isoentropic expansion. We routinely run with temperatures of about 3 or 4 degrees Kelvin using argon here. So we make these water molecules, these clusters of dimers, trimers, tetramers, pentamers, and we cool them to say 3 or 4 degrees Kelvin. Then we study them with a lab full of lasers. And the region of the spectrum that we work in typically is a strange region here in the far infrared. This is the electromagnetic spectrum. Almost everything we know about it occurs in this little bandwidth here that we call visible, that our eyes are sensitive to. But our lab is working way down here in the far infrared, and we're looking at the bends and stretching motions of these hydrogen bonds. So there's a lot of laser technology here that is actually my favorite thing, but I don't want to talk about that here. This is Susan Strawn, one of my early students. This is one of our carbon dioxide lasers. But let me just show you some results. So this is the water pentamer. This is the most stable form that 5 water molecules interacting with one another adopt. Make this beautiful 5-membered ring. Nearly planar, almost tetrahedral angles. It's essentially an on-strain ring system. Every water molecule here is acting as a single donor of hydrogen bond here, the hydrogen, and a single acceptor of the hydrogen bond. This made the cover of Science. Actually, I'm very proud of this because, as you know, how many of you read Science? Science usually features bugs on the cover. To beat out a bug on the cover of Science is no small accomplishment. So I'm very proud of this. Actually, this water pentamer has gotten a lot of attention. It has just become the cover of the latest textbook in physical chemistry by Raymond Chang. That's nice. Here's what 6 water molecules looks like, and some of my colleagues caught the press's attention with this. So 6 water molecules adopts this hollow cage structure. Now water molecules here begin to take on the ability to solvate things. So you can imagine some hydrophobic molecule or hydrophilic molecule going inside of this cage formed by the 6 water molecules. So my colleagues, actually David Clary from University College London, my theoretical collaborator, named this the world's smallest drop of water because of this ability to solvate in that hollow cage. And he managed to get this on the European press and also on the European radio stations. They were doing quiz shows, calling up people at home and asking them, what is the smallest drop of water for 1,000 pounds or so? And the answer is the water hexamer. Should you ever get such a cool recently, there's some very beautiful work, not from my group, but from Roger Miller's group at the University of North Carolina. They found another form of the water hexamer, which is a 6-membered ring. So this complements our study of the 5-membered ring. And he calls this, picking up on the David Clary, he calls this the smallest piece of ice, because I remember I told you ice had these 6-membered rings. Hexagonal rings, that's where ice 1H gets its name from. That's why snowflakes have this 6-fold symmetry. He studied the properties of this cyclic water hexamer, not the most energetically stable form that he can make. That's the smallest chunk of ice 1H, he should have said. Another friend of mine, Tim Sweer at Purdue, has studied this. Water octamer. This is the most stable form that 8 water molecules adopt. Makes a slightly distorted cube. Very beautiful structure. He calls this the world's smallest ice cube.
What pressure is this? Is it under very high pressure?
No, these are all in supersonic beams at 3 degrees Kelvin in vacuum. And they're not equilibrium experiments. These are supersonic beams. Okay, so the idea then is to study these kinds of small water clusters in great gory detail with a lab full of lasers, computers, collaborate with theoreticians, and we've been doing this for 10 years. We've actually made enormous progress. The goal of this is to study these water clusters so we can develop an understanding of the liquid and the solid. And one of the immediate goals is to develop what I call a universal water potential from our spectroscopic study of these clusters. I call these VRT spectra for vibration, rotation, tone to decay. The goal of this is to produce a flexible, polarizable water diamond potential with all the intricate corrections that will correctly reproduce the properties of the liquids and solids when we do computer simulations, which no potential that exists today will do. And the key to this whole operation is to measure these vibrations of the water dynamo, surprisingly. There are 6 of them. To measure all these different, these are the vibrations of the hydrogen bond in water dynamos. And we've measured all of these except one. And this, we've just published our first installment of this in 1999 in Science, here if you're interested. Spectroscopic determination of the water pair potential. So this is a big step toward having a quantitatively accurate computer model for liquid water. We call our potential VRT-ASW, practically perfect polarizable pair potential. So you can see again the influence of my daughters. This is Mary Poppins language, right? So this is our potential, this is the name of our potential. And we're perfecting this with subsequent versions. All of this has come from the study of the water dimer. And another thing that we're doing right now is using this water trimer to make what we call the 3-body correction. So it's my intention, it's a technical detail for the experts here. The water dimer tells us how pairs of water molecules interact. And that turns out to be the single most important element of the water force field. It's the pairwise interactions of water molecules. 2 at a time is responsible for most of the properties of liquid water. Surprising. This is very surprising at first. And I get lots of tomatoes thrown at me from my theoretical colleagues who are expert in this, but this is correct. And that's most of the force field that we're trying to get. The remainder are what we would call 3-body corrections, that is 3 water molecules interacting at a time. And we get the physics of that by studying this simple object here, the water trimer. And we have a huge amount of data for this as well, and we're just in the process of trying to put this all together, collaborating with theoreticians. So that's where this all stands. I would say we're a few years from publishing the potential that will describe liquid and solid water better than anything out there. Hopefully much, much better. Okay, I need to do this. So one practical aspect of this work on small water clusters comes in the context of weather, perhaps we can say. This is one of my favorite photographs. Nobody will ever get this here unless you can read fine print better than I can. Did you see this? Who knows what this is? You saw it? This is a beautiful photograph that came in the newspaper. This is the Space Needle in Seattle. And this is in a rainstorm. I guess a light rain shower. And look at that beautiful photography. There's the reflection of the Space Needle and all these water droplets. Amazing piece of photography. But anyway, so this work that we've been doing on water clusters has one practical application that just made the cover of the Journal of Physical Chemistry months ago. And that is from the detailed knowledge that we've assimilated and are pretending to combine this with statistical mechanics and predict the concentration of water dimers and larger clusters in the atmosphere under any conditions. You tell me the conditions of the atmosphere, namely temperature, relative humidity, and so on. I can tell you the dimer concentrations. So I think we have answered a question that's been thrown out for many, many years. That is, what is the role of water dimers and trimers in atmospheric chemistry? There have been many attempts to answer this, but they haven't had the information that they could do this with. I think we can now. And the bottom line is, in the marine layer, where one gets a very high concentration of water monomers, and in the tropics, these water clusters are likely to play an important role in the chemistry. They constitute up to 2 or 3/10% of the total water density in those situations. So this is a new idea that remains to be explored in atmospheric chemistry and so on. Oh, I could go on, and I just love to talk about water. I love to talk about water. I think maybe I'll skip some of this stuff and talk about some poetry. I like this one, Byron. Till taught by pain, men know not what good water's worth. This is my philosophy of running my research group. This is one of my graduate students here, David Cook. So we have to teach them what good water's worth. Then they can do all these nice experiments. Here's something from Carl Sandburg here. This is very interesting. Carl Sandburg said, when water turns ice, does it remember that one time it was water? When ice turns back into water, does it remember it was ice? Some people took this too seriously. Here is such a man. This is Professor Ben Benisti from, I forgot what university in France, but he was very popular a decade ago. And he is the originator of the latest version of, what do you call this? The word has escaped. The use of drugs diluted to tiny, tiny amounts of homeopathy. And he is the latest guru, the latest wave of homeopathy came from Ben Benisti. He did these experiments that were published in Nature a decade ago that claimed he measured some drug activity in an enzyme, and then they kept diluting the system until they had diluted the system so much that on the average there was not a single molecule of the enzyme left in it, and yet the biological activity was still appearing. And the take-home message of that was water has memory. Water remembers, its structure remembers this enzyme being in it, and so you can carry out biological reactions just from the memory of water. This guy read Carl Sandburg and took him very seriously. Beautiful idea. Unfortunately, like most radical ideas in science, it was patently wrong. No other laboratory in the world has ever been able to reproduce any of Ben Benisti's results. And sadly, this very exciting idea can't be substantiated by anybody else in the world. But Ben Benisti has not given up. Now, for this work on water memory, he was awarded the prize from Harvard University. Has this thing called the Ig Nobel Prizes. Have you ever heard of the Ig Nobel Prizes? These are the anti-Nobel Prizes for the dumbest discovery in science in the latest. He won an Ig Nobel for his water memory work. That didn't slow him down at all. In the last year, Ben Benisti published stuff not in Science and Nature, but in other places where he not only he believes water has memory, but he can email his water memory to anybody in the world, and you can transfer this memory into your water. And people from Harvard University reported as saying, yes, Professor Ben Benisti is very likely, for this work he did win. He is actually the only person in history to win 2 Ig Nobel Prizes. He won a second Ig Nobel Prize for being able to email the memory of water. And Dudley Hirschbach, Nobel Prize winner in chemistry from Harvard, was quoted in the media saying, yes, and with this type of work, Professor Ben Benisti is very likely to win a 3rd. He took the poetry a little too serious. But water has a romantic aspect as well that we all know about. Here are some of them. Water has captured people's romance from day one, right? We all know about these things, fountain of youth. You've heard of polywater, I suspect. Here's the water memory issue with memory. You've heard about cold fusion. That was a water as the universal energy source. That was a flop. Water as a fuel still keeps coming back. And since for the last 10 years I've been working in water, I have a huge email file of people sending me letters on every subject you can imagine relating to water. How many of you have heard of Willard water? Have you heard of Willard water? You can go buy Willard water if you go up to Calistoga and go to Old Faithful of Calistoga. They still sell Willard water. People used to go peddle this stuff door to door as one of the million versions of snake oil that water took. In fact, one of my wife's relatives used to sell Willard water, right? Who was it? Your brother? No.
No.
So, a friend of hers, he said, saw loaded water. Anyway, water has captured people's romance. This is the latest. This is the latest thing. I have got a big old file of email on this subject here. This is the latest. This appeared in the LA Times about 3 weeks, about a month ago, by this columnist, Rosie Mescal. She called me up one day and asked if she could interview me about a subject that people have been telling her about. And this subject is structured water. This is the latest rage, structured water. And I have fielded a whole bunch of stuff about structured water. In this particular case, the structured water, they claim, is built on these 6-membered rings that I told you about. Now there's a company, actually there are a bunch of companies that claim they can deliver to you a beaker full of water made up of these 6-membered rings that I showed, 6-membered clusters of water, and that this has all sorts of magical properties. That's what this is all about. So I argued and argued. She presented all the arguments from this company, and I finished this discussion simply saying here, okay, look, I was trying to explain to her why this doesn't make sense. That you can't have a beaker with water, 6-membered rings of water, and it won't stay that way for more than 1 picosecond, or 1 times 10 to minus 12 seconds. Trying to explain how this works. Finally, I concluded by saying, okay, if these guys are right, if they can really, oh, I'm sorry, this was pentawater, this was 5-membered rings. This company makes 5-membered. There are many that make 6-membered. I said, if they can really do this, they should send the results to Stockholm, because they're definitely going to win a Nobel Prize. If you can do that, they will win a Nobel Prize, because they will have uncovered really new physics. Here's, let's see, what's this one? Here's a letter that I got. This is from Chang Jin Kim, president of Hexagonal Water Company in Korea. I have devoted 15 years of my life to make better water, and I have a patent for a machine to make hexagonal structure, da-da-da-da. Okay. Here's Penny Chen from Malaysia. They use infrared ray can split water clusters into tiny molecules. I get this stuff all the time, and when I argue with these people, this is the universal attitude. They all say, "You're one of these conservative scientists. You just don't know a good idea when you hear one." And you know, that is the quandary of a scientist, is that you can err in either direction. Many scientists are just far too conservative. They don't accept new ideas. On the other hand, you have to apply really rigorous standards of evidence. You can't just believe in it. You have to very, very carefully test things. You can only accept those results that stand many different tests, such as the Benveniste results, fail. So many of these romantic ideas of water just don't hold up. They're very interesting, very intriguing. They just don't hold up to modern chemistry and physics ideas. But there are many questions involving water that I think are romantic, and this is the latest science book on water here, written by the late G. Willis Robinson, who had a great interest in water. A very good book, summarizes a great deal of what has been learned from the inception of science about water in this book. And in the introduction to this book, published in 1996, G. Willis Robinson, in the introduction he makes this statement right here. For all these reasons, liquid water remains therefore the most important unsolved problem in science. To me, that's romantic enough. I'm captured by the romance of this, trying to solve the scientific mysteries of water. And we're trying to do this by the cluster connection, building up water, liquid water, one step at a time. Thank you very much for listening.
We have time for questions.
I'm particularly interested in the properties of water to
oxygen and give it back to, obviously, the living creatures. Can you tell us anything about that?
Water, I didn't talk much at all about the unique solvent properties of water, but they are in fact unique. Water is a polar molecule, which is the origin of its hydrogen bonding. It has a positive end and a negative end, okay? And therefore, it's a very good solvent for polar solutes, salts, alcohols dissolve very well in water. But water also does a good job on many other things. It has a very wide variety of solvent properties. On the other extreme, water exhibits something called the hydrophobic effect, which is a restructuring of water when it encounters, let's say, hydrocarbons or biological polymers, and it's this hydrophobic interaction, hydrophobic solvation that's really why we're here. This is how biological membranes form, which give rise to cells and all of that. Now, as far as oxygen goes, oxygen is clearly nonpolar, and the nature of the interaction between water clusters and oxygen, that's a very interesting point. I have to think about it.
It's essential to all life in the sea.
Of course, and to us.
I'll come from this side. Is there any questions?
I have a question on that statement about the unsolved problem. Whose statement was?
This is in the introduction to this latest book, latest scientific book on water. G. Waltz Robinson, Water and Chemistry and Biology, published 1996, book scientific books.
Is it a valid question, do you think?
Oh yeah, absolutely. Well, you know, whether this is a value judgment, clearly, right?
Well, would Wittgenstein set it aside as nonsense, or would he? Someone like Wittgenstein, would they put it aside as nonsense?
I don't know who that is.
He's a philosopher.
Who?
Ludwig Wittgenstein.
He's a mathematician.
Mathematician.
I don't know that. That's my ignorance. Never
Well,
heard of him.
it's the same idea. You begin to do science by asking, is the question, is the subject really even sensible? That's the...
Well, you know, scientists tend to be very practical creatures. Scientists live only in the realm of evidence. We're trying to be we're trying to solve a very practical problem here. And we only accept truth when it's testable against experiments. So that's a relatively narrow domain of human thought. And those kinds of questions fall outside of science. The question you say, is the question valid? That's outside. I mean, that's like, that's exploring, that's like the ontological versus the cosmological and so on. That's outside of our rather narrow realm of thought here as a practical scientist. I'm trying to answer specific questions about this with water.
Yep.
You showed that solid waters can form two amorphous phases. Are they
Two amorphous solids.
solids? Are they structurally related to the amorphous liquid?
Brilliant question. How do you know about this? What's your background?
Material science.
So you know about what? Do you know about this controversy on two different forms of liquid
But I
water?
never got a straight answer.
Yeah. Okay, this is one of the really interesting and raging controversies about water that it's a little more complicated than I wanted to go into, but I showed you these pictures of the two amorphous forms of ice. Amorphous means glass-like, no long-range order. Okay? Like a liquid. It's like if you can take a snapshot of the liquid, that's what an amorphous solid would look like. Okay, there's a group of theoreticians who predict that there's not one kind of liquid water, but there are actually two types of liquid water. Just like there's a high-density amorphous solid and a low-density amorphous solid, there is also predicted to be a high-density liquid and a low-density liquid connected by what we call a first-order phase transition, a line of which terminates in the second critical point for the liquid in the deeply supercooled region. This is a really exciting prediction, and there is experimental support for it, but it's got a long ways to go before it's strongly supported. Really interesting question. Maybe that's the most interesting question of all right now in the science of water.
I was surprised, maybe I should have been.
I can't hear you.
I was surprised, maybe I should have been, but on the graphs you showed of the potentials, the theoretical potential versus the measured experimental.
Calculations versus measured, right.
But the measured, the experimental, made a nice smooth curve there, basically predicted we're all over the place.
Well, that's the problem, that there are about 1,000 published force fields that are computer models for water, and they all do some things well. None of them can calculate the properties of water over large temperature ranges or anything like that. So they all are very limited in scope and accuracy.
I kind of would have expected the theoretical ones.
No. It's extremely hard to model liquid water. The reason it's hard is because the strong tetrahedral, because only 10% of the hydrogen bonds are broken relative to the solid. It's a very complicated network. Really hard to describe that theoretically. That's the problem.
Yes?
Can I ask what may be a sociological question? Because you asked us at the outset what makes water wet. As far as I can tell, you didn't really address the question. You could have titled the subject lots of things. Why do you pick it up?
Because it gives me a chance to squirt the audience. Would you like to participate in the squirting?
Well, I'd rather be wet by ethanol.
Illegal on campus.
Much more fun.
Some more question here? Yeah.
What is the molecular structure or the forms of the cluster of water at the air-water interface?
At the air-water interface, that's a really good question. Actually, one of the things my group has been working on for about 3 years now, is the study of the liquid water surface. More rigorously, the liquid vapor interface. This is another of the great unknowns about water. The nature of the liquid water surface is not at all well characterized, because it's very hard to approach this experimentally. Surface science techniques, which have made enormous progress in the last several decades, are primarily ultra-high vacuum techniques. And liquid water, of course, is very volatile, has high vapor pressures. So none of that stuff works. We're just starting to answer such questions. We have a paper, we have one paper out in the Journal of Physical Chemistry. We have another paper submitted to Science as of about a week ago that says the nature of the liquid water surface is dominated by two populations of hydrogen bonded waters. One of them is perhaps you call a single donor. It has one OH sticking up out of the surface like that. Professor Shen from the physics department, who's just finished giving the physical chemistry lecture that I missed in chemistry, first discovered this free OH bond sticking out of the water surface. That's about 30% of the surface molecules. We've discovered another form, which is a form of water with both hydrogens sticking out of the surface. We call those pure acceptors. Those have never been identified before. We think about 30% of the surface molecules are like that. The remaining would then be what you might call ice-like, making 4 bonds in the usual sort of way. So in summary, these sort of detailed questions on what is the structure, what is the molecular nature of the liquid water surface are just being answered now with modern experiments.
People have been dousing water for hundreds of years.
Yeah, I gotta make a slide.
It seems like a technology that's there, but has there been any scientific work on that?
I'm pretty ignorant about that whole area. I would be surprised if there's any credible scientific evidence for dowsing. However, it is amazing how widespread this dowsing stuff is.
People will hire. People will hire a dowser long before they hire.
I know this. That's what I mean. This is. I found this out when my wife and I were thinking about buying property up in where was it? Somewhere up north on Highway 101, and the realtors say, well, whether or not there's water on the property is a really crucial issue. They say, well, we can put you in touch with local dowsers who are, you know, water witches, as they call them. Very widespread. I would seriously doubt if there's any evidence for it. If there is, I have no idea how this would work.
You could say something about dangling bonds on carbon, for example. Take two pieces of carbon, like say polished diamond substance, you put them together in electric water. They exhibit very high electricity. Low coefficient of friction. And I'm very interested in if this only occurs with carbon and water, or whether it occurs with other solids and water.
I'm afraid you got me in an area that I know nothing about. I really know absolutely nothing. I mean, I know a little bit about dangling bonds and graphite and things like that. I don't know any of these studies of that sort. It sounds very interesting.
It is essentially first strike technical important.
Yeah, I would think so.
Because you don't need another material as a lubricant. You put liquid water on a diamond-like amorphous surface, and you prepare the surface right, you get a very low coefficient of friction. If you don't prepare it right, you get high coefficient of friction.
Just the fact that the friction would be different depending on how you prepare it is very interesting.
Yeah, these are amorphous.
Is this published?
As you know, it's amorphous.
Amorphous diamond? Or?
Diamond-like carbon has some hydrogen in it.
Yeah.
But if you put it in liquid water and you prepare this film properly, you get this very low coefficient of friction, below 0.01. Some people have measured 0.201. But if you do deviate from that recipe, you don't get that low coefficient of friction. You get a high coefficient or variable.
Is this published?
Yeah, it's published, but not in the kind of work you're doing.
I'd like to read about this. Could you, that's my email address. Could you
Well,
send it?
I would have to send this back to you. I can't quote it from my head. That's a research.
Any information you have on that would be very interesting, not only to me, but my colleague in chemistry, Gabor Samarjai, as a specialist in molecular lubrication. He would be very interested in this. Maybe he knows about it.
I'll write you the reference.
That's very interesting. The fact that the friction would even change depending on how you prepare it is very interesting.
Yeah.
Hard to measure, so it could be wrong too. So.
Oh, yes.
One final question?
Yeah, the frequencies, I don't understand that. Could you explain like how water works on frequencies?
You mean the slide that I showed about the vibration?
Yeah, how does that work? Like, is that really important to water structure?
No. This refers to when I take two water molecules and I form a hydrogen bond between them to make the water diamond. Okay, that there are 6 different ways that object can vibrate. These are called normal modes. And each type of vibration has a specific characteristic frequency. And that frequency is arguably the best way to characterize the force field between these two waters. And that's why we sought to measure all those frequencies. They're the best measure of the force field, and that's what we were after. So they characterize the force field, but they have no significance really beyond that.
Right. So can you create force fields? Can you make force fields in water?
Not beyond what already exists. What we're trying to do is study the force field that exists among water molecules, because that's the essential feature. The strong tetrahedral hydrogen bonding is the force field of water, and it's what gives rise to all these properties.
So there's no way you could possibly change that?
Oh, sure, you can certainly change that. I mean, you can take a very high power laser and you can focus it into water, create enormously high electric fields. You can do that in any type of matter.
So if you were making an electromagnetic field, then you could change the structure of the water?
Yeah, definitely. This is called pre-dissociation experiment. You can blow things apart. You can blow any substance apart with lasers of appropriate power. There's nothing new there. the laser electric field just exceeds the forces holding the system together, you can blow it apart. But if you're going in the direction of, can I restructure water with electric fields? Can I cause it to form a new structure? Is this what you're alluding to? Okay, that's very interesting. Now, one of the groups of people that I have worked with in the past, actually the last time I gave a lecture like this on this campus, 2 years ago, came up to me afterward and asked me a very similar question, and I said no. And she was working with a company that manufactures a water structuring device that they claim, you plug this thing in the wall, it applies very high electric fields to water, and what comes out of this thing is water with this is another form of the structured water controversy. Right. And there's a whole literature here that she showed me that you can take these devices and water golf courses with water run through these on 10% of the water that they normally take. You can water gardens with 10%, 90% less water in all this. And I said, I don't believe a word of this. So she brought me in with the device to inspect myself, and I took this device, took it apart. I still have no idea how this thing is supposed to work because it made absolutely no physical sense. But that was an attempt to restructure water, but it made no physical sense whatsoever. None at all. But it sold a lot of copies, so it made financial sense. A lot of people bought this, but it didn't make any sense. Hey, good way.
So before we adjourn, I just want to make a quick announcement. This fall coming fall, starting in September, we will have another series of these 4 talks for the fall semester with Professor Joe Sachs from our law school. We talk about legal matters and so forth. We have some very good speakers lined up for the fall. You will all get the announcement through email or flyers and things like that. And when we invited Professor Saykally to give a talk today, this is exactly the kind of talk I was expecting. Simple public education about the mysteries of water, bringing science to the common curious mind to understand. And what is so interesting is that despite the sophistication of research, the results are amenable for us to understand in simple mental images. And that is the whole idea of bringing science and the humanities together, for which we thank Professor Saykally.